This is worksheet 2 from our chapter on electric potential. It says in the picture tube we have electrons that are accelerated from rest. So right away we see that we have the word electron. We know the mass of an electron. The mass of an electron is a given value, 9.1 times 10 to the negative 31st power. That's a mass that is measured in kilograms. In addition, I know the charge of an electron, also a given. I know that it's a negative. The charge is 1.6 times 10 to the negative 19th power. That's going to be a charge measured in coulombs. I mentioned that it's negative. I'm going to apply that fact when I decide which direction it's going to move. It says that it's at rest, so our initial velocity is going to be 0. It's going to be accelerated through a potential of 22,000 volts. So in addition to the information for an electron, I also know that my potential is going to be 22,000 volts. So recognizing that my potential is the letter V. We're trying to figure out the speed, which is going to be lowercase v. If we want, we could even call it v final. We're trying to figure out the final velocity when this negatively charged electron strikes the opposite plate. So if I look at the question here, it says to draw in the charges on the plates. These arrows given to us are actually electric field arrows. They point in the direction of force on a positive test charge. Now, even though we have a negative electron, we still envision having a positive test charge, and a positive test charge being moved to the right would be repelled by positives on the left. It would be attracted to negatives that are on the right. So those are the electric field lines caused by those charged plates. So what's going to happen to our electron? Our electron is going to feel a repulsive force from that negative plate, which means that it is going to be pushed and therefore accelerated to the left. We could use forces in kinematics, but we're given information that allows us to use energy instead, which is much more convenient. So at the beginning, I have no kinetic energy, but I do have energy built up because of the position of our negative charge. So I have potential energy, original, caused by my electric field. When it strikes the opposite plate over here, it's going to have no more potential energy, but at this point it will be moving, which means we're going to have some final amount of kinetic energy. So a very standard conservation of energy type question. Our potential energy, I have Q times E times D. However, I am not given E or D. But what I am given is I am given a potential. That potential is my energy ratio. So if I take the amount of charge and I multiply that by the energy ratio, energy per charge ratio, I can use that to find my potential. I have 1/2 mv squared. And again, I can put in a final right there if that makes it a little bit more obvious to us. And so now I'm able to put in my values. I have a value for charge, 1.6 times 10 to the negative 19th. I don't need to worry about the negative sign. I've already used that to determine that our charge is going to accelerate to the left. My potential is the 22,000 value. And then I have my 1/2, the mass of my electron, 9.1 times 10 to the negative 31st power, multiplied by our final velocity, the value we're trying to find, squared. Calculating our final velocity, we end up with a very large number, which is expected because our electron is so small. It doesn't take a lot of force to get this accelerating at a great rate. We end up with about 8.8 times 10 to the, it looks like 7th power. And that's going to be in meters per second. Question number 2. An electron is placed, once again, right there, electron right out of the gate. I know that value. I have them written down previously, so midway between two parallel conducting plates. We have a separation of 3 millimeters. We're going to want to make sure that we're using meters instead of millimeters. So this distance right here is going to be 0.003 meters. We have the terminals of a battery, 12 volts. That's going to be the potential difference between the positive and negative end of our battery, which means we're going to have that same change in potential, or that same difference in potential, when I compare the two plates that are connected to those opposite ends of the battery. What is the direction and the magnitude of the electric field? I have a potential equation equals E times D, and so I'm given my 12 volts. I do not know what my electric field value is, put my vector arrow there, but I do know that my distance is going to be 0.003. And so we calculate our electric field as 4,000. I have newtons per coulomb from the previous chapter. I can also look at it as 12 volts divided by 0.003 meters. So my other possibility would be a volt per meter as a unit. Now that takes care of the magnitude. The direction is going to be where a positive would go. Here I have a positive plate because it's connected to the positive end of my battery, which means I have a negative here. A positive plate placed in between these two plates would repel a positive and attract a negative. So that right there is the direction of my electric field. So perhaps in my answer I can include the word right as it pertains to my picture. I could say toward the negative plate. How much work would be done by moving the electron from the midpoint to the surface of the plate? So I'm going from right here, and I'm going to take this and I'm going to move it over here to the negative plate. That's something that the negative wouldn't do on its own, which means I have to apply a force, which means I'm going to do work on the particle and give it energy. So if I can figure out the amount of energy change that we experience, that will equal the work that I have done. So I have charge of an electron. I have the electric field, which we have just calculated, and now I can look at the change in position of my particle. So I have the charge of my electron. That should be a 9 there. There we go. I have an electric field, which was calculated as 4,000. Now, I do not use the 0.003. That's the difference between, or the distance between both plates. I'm only moving half of that. So I could think of this as half of the distance between my plates. I could do that work in my head and just put in 0.0015. So doing that will give me the amount of energy that we have gained, which would be the amount of work that we must have done. So the amount of work done was 9.6 times 10 to the negative 19th joules. Small amount of work being done because I'm moving a rather small particle. If the electron, part C, were released from a point midway between the plates, what would be its velocity when it struck the positive plate? So instead of pushing it to the right like we did here, what we're looking at is what happens if we have it at the midpoint and we just let it go. Well, the electric force is going to move this thing over here to that positive plate. The energy that we have at this location is going to turn into kinetic when we reach our location here. This is just like question number 1, which means the potential energy that we had at the beginning is going to equal kinetic energy at the end. I already have the amount of energy here. So I already have a value that I can use, and so all I have to worry about is the right-hand side of this equation, which is going to be 1/2 mv squared. So I end up with 9.6 times 10 to the negative 19th. That's going to equal 1/2 times the mass. We're still working with an electron, so that's going to be 9.1 times 10 to the negative 31st power times final velocity squared. If it helps me to visualize this as energy with a final on there, then I do it. Our final velocity ends up being 1.45 times 10 to the 6th power, and let's not forget our unit of meters per second because we're talking about a velocity. Part D asks if the potential difference were doubled, how much faster would our velocity be? Well, I know that my amount of potential energy that we're going to have is going to be proportional to that amount of potential. So if we double our potential, we'll double our energy. I know that that's going to relate to my kinetic energy, so I'll have twice the kinetic energy. Now, because I have a v squared, if I'm going to take my kinetic energy and double it, that means that my v squared is proportional to k, which means if I'm going to have my k value double, I cannot double my velocity because that velocity is going to be squared. So I need to see an increase of square root of 2 times my original velocity. So our new velocity would not be doubled. It would only be 2.05 times 10 to the 6th power, once again meters per second. Now, if looking at these relationships doesn't make a lot of sense, you can always just start over all the way back up here at A and plug in a 24. You'll get a new amount of work done, which is going to be twice the size, and then you can plug it in right here. Looking at question number 3, we have a beam of protons. Rather than try to think of this as a bunch of protons flying through the air, it's best if we just think about this as a single proton. So if I can ask myself what a single proton would do in going through this scenario, I'll be able to determine what the whole beam will do. The mass of our proton is a known value of 1.67 times 10 to the negative 27th unit in kilograms. And just like with our electron, we do know the charge of our proton. It's going to be 1.6 times 10 to the negative 19th coulombs. So there is my mass and my charge. We see that we have an initial velocity. So that tells me that we're going to start off with some initial kinetic energy. It says this plate has the potential that is 4 kilovolts. That's 4,000 volts. And we're shooting it to a plate that has a higher potential than the beam itself. So we're going to a higher potential energy. So if I set up a conservation of energy equation, I have potential and kinetic at the beginning. I want to consider potential and kinetic at the end. It says we're moving at the beginning, so I know that I'm going to have some kinetic energy at the beginning. I'm asked about the velocity, so I assume there's going to be some kinetic energy at the end. It says we're launching or firing these particles to a position that is has a higher potential. So what I can do is I can just simply say this right here is 0. I start with no potential energy, and this change right here is going to go into producing a final potential energy. If I use my gravity analogy, we're throwing this thing up into the air. I expect it to slow down. And if I have some kinetic energy already, and now I'm going to have some potential after that, that means this kinetic right here is going to have to drop, which means my speed will be reduced. The equation for my kinetic energy is going to be 1/2 mv original squared. That's going to equal, I've got QED as a possibility, but it looks like we're given volts. So just like with question number 1, I am instead going to go with QV. and then I have my 1/2 mass final velocity squared. So if I want to put in my values, 1/2 mass of my proton, 1.67 times 10 to the negative 27th. Original velocity is given to me up here as 5 times 10 to the 6th. 5 times 10 to the 6th power. And that's going to equal the charge of our proton, 1.6 times 10 to the negative 19th power, multiplied by the potential. We're given the potential of 4 kilovolts, which is 4,000. And now I have 1/2 that same mass of my proton. These scientific notation numbers do take up some space when you're writing them out. And final velocity squared. It's a lot to write down right there, but we end up with a final velocity. Our final velocity is 4.9 times 10 to the 6th meters per second. I expect it to slow down. It goes from 5 down to 4.9, so I see that it is indeed going to be slowing down as it goes to a higher potential. Next, we have question number 4. This references the experiment performed by Robert Millikan years ago to determine what the charge of a single electron or proton is. So what forces act on our suspended drop? So over here, I'm going to draw a force diagram on my drop. This drop, while it is small, is large enough to have relevant force of gravity acting on it. So this force of gravity I can calculate by doing m times g. It's going to remain suspended because there is an electric force pointing up. These two are going to be equal, and so that's going to allow me to, well, do just that, put them as equal when I do my problem. What forces act on the suspended drop? Draw a force diagram that supports your answer. So question A, we are done. Question B, assuming the mass of the oil drop is, and we give us the mass right here, the potential difference between the plates is, and the separation between the plates is, I've got my values listed there. What is the charge on the drop? So going back up to my diagram way up here, my electric force is going to be our charge multiplied by the field. It's kind of a crazy multiplication symbol there. Why don't I do that right there? It looks a little better. Yeah, maybe not. I need to find my electric field. To find my electric field, I have an equation that says that the potential difference is equal to our electric field multiplied by the distance between my plates or my locations. So I have 1630 as the voltage given. I need to find my electric field. That way I can figure out where this point, the force on my particle. And the distance between the plates is 0.02. Students will sometimes look at the diagram and say it's only halfway between the plates. Shouldn't I use half of the distance? The answer is no, because this potential right here, this 1630, that is the potential difference between my two plates, and my two plates are separated by 0.02. So I need to make sure that I am using the proper distance. So if I take 1630, I divide it by 0.02, and we end up with an electric field that is equal to 81,500 newtons per coulomb. We're quite used to seeing electric fields that are rather large, because if you actually had 1 full coulomb of charge, you would expect to have a very large force, because 1 coulomb is a lot. So coming back to actually answer part B, what is the charge on the drop? Well, my two forces are equal to each other. I now have 3 out of the 4 variables. M is given, G we use as 10, charge is what we are looking for, and I just calculated what my electric field is going to be. So the mass is given as 4 times 10 to the negative 15th. We're going to multiply that by 10, and that's going to equal our unknown charge multiplied by 81,500 newtons per coulomb. I calculate my charge to be 4.9 times 10 to the negative 19th coulombs. I have a negative plate right here, which means to have an upward force, I must have a negative amount of charge. So technically, I should have a negative 4.9 times 10 to the negative 19th coulombs. If we scroll up a little bit here, how many excess electrons are on this drop? Well, if this right here is the amount of charge I have, that's my total. To figure out how many electrons will make up that total, I take my total and I divide it by the value of a single. So I have this as the total amount of charge. A single electron is negative 1.6 times 10 to the negative 19th. When I do this, the negatives cancel out. I cannot have a negative amount of electrons, and technically my answer, according to my calculator, is going to be 3.07 or something along those lines. The question says, how many electrons do I have? Well, I have 3.07. I cannot have 0.07 electrons, so I just round that off. I must have 3 excess electrons. In the past, students have asked, should I subtract one away? No, because to get my 4.9, I need to have all 3 of these as unbalanced extra electrons, electrons that are not being canceled out by a proton. And that leaves us with question number 5. It says we have an unknown charged particle of an electron or a proton. Well, right away, I know that I have a charge that's going to be 1.6 times 10 to the negative 19th, because that's the charge of an electron or a proton. So I do have that. And what might actually be useful is that the masses of these two things are going to be different. So that's one way I will be able to distinguish if I have an electron or a proton. It is released from rest, which means it has 0 kinetic energy at the beginning, and it is going to accelerate, which means it must have potential energy causing this particle. Looking at the diagram, there's our particle right there at A. We're going to release this, and it is going to get fired upward until it reaches the other side. So we must have a lot of potential energy here. When we get to this plate, we'll have no more potential energy, but it will have turned into kinetic energy. Kinetic energy has mass in the equation, so that's going to be helpful. It says the particle emerges through the hole at point B with a final speed, they don't use the word final, but a final speed of 1.4. So I start at rest and have just potential. I'm going to go through here. I'm going to have some kinetic because of this velocity. That should be the word is the unknown particle an electron or a proton? Justify your answer. The only difference besides being positive or negative, and that isn't useful yet because I don't know the charges of my plates, positive or negative, I don't know. So the only other way to determine that is going to be the mass. So we already said we started off with some potential at the beginning. I can call that initial if I want, or just call it U. We're going to have some kinetic at the end. And so I look over here, what do I have? I have V equals 100 volts. I know if I take Q times V, that will give me my energy. I have the charge of my particle, I have V, and that's going to equal 1/2 the mass of my particle times this final velocity, which is a given, squared. So 1.6 times 10 to the negative 19th. The potential difference is 100, or the voltage is 100. That's going to equal 1/2 unknown mass, but once I know my mass, I will know what my particle must be. 1.4 times 10 to the 5th power. Don't forget to square that. Using my calculator, I get an answer that says 1.63 times 10 to the negative 27th kilograms. 1.63 seems awfully close to 1.67. I think that's close enough to know that this must be a proton because the size matches. Which plate is the positively charged plate? I'm going to erase my question marks here. If I place a positive here and it goes shooting upward, I must have a positive plate down here to repel it. I also have a negative plate up top to attract it. So that was worksheet number 2.